Mr. Chairman, dear colleagues, good morning. My name is Dr. Aziz Arbai, representing l'École des Nouvelles Sciences d'Ingénierie, ainsi in Tangier, Morocco. It is a great honor to be here today at National Technical University of Athens for APEX. Today I'm going to present a theoretical and practical breakthrough in robotics. Analytic matrix solution for real-time UEV drone attitude control. We will see how we can move beyond the classical Rodriguez formula to natively integrate damping and friction into our flight controller. Let's start with the core challenge. Autonomous aerial and underwater vehicle rely entirely on the continued integration of their orientation to maintain flight stability. A flight controller needs to adapt this attitude hundreds of thousands of times per second. The problem is that classical approaches are failing us. Other angles suffer from gimbal lock singularity, and when engineers turn to numerical integrator like Taylor series or range Kuta, they face massive CPU drainage and more critical numerical drives over long mission. Our goal is simple: to guarantee the absolute mathematical integrity of the rotation matrix, ensuring the drone spatial coordinate system never deform. To understand the root of the problem, we must look at the classical rigid body dynamics. The evolution of the rotation matrix RT is driven by the skew symmetric velocity matrix omega. For nearly 2 centuries, the robotics community has used the Rodriguez rotation formula to solve this. But there is a massive classical flaw. Rodriguez formula strictly assumes a purely conservative system. It requires the dynamic matrix to be perfectly skew symmetric. In the real world, drones experience aerodynamic drag, rotor friction, and active control damping. These non-conservative forces make the dynamic matrix asymmetric. When this happens, Rodriguez formula completely breaks down, forcing embedded system to rely on heavy iterative numerical fallbacks. To solve this without numerical iteration, we turn to pure algebra, specifically the Killen-Hamilton theorem. The theorem states that every 3 by 3 matrix satisfies its own characteristic equation or own characteristic polynomial. This fundamental property allows us to take the infinite Taylor series of the matrix exponential and strictly truncate into a finite degree 2 polynomial. As you can see on the screen, the exponential of ET becomes a simple linear combination of the identity matrix E and E squared. The paradigm shifts dramatically here. We transition from computational complexity of theta in qubit down to theta 1 constant time. The only remaining challenge is to find this time-dependent scalar coefficient alpha 0, alpha 1, and alpha 2. To compute this alpha coefficient analytically, we project the scalar eigenvalue of the dynamic matrix onto a linear van der Waals system. By inverting this system, we completely isolate the coefficient. But what about the complex roots caused by oscillatory damping? By mathematically applying Euler's identity to the complex conjugate roots, the imaginary components perfectly cancel each other out. The result is beautiful. We obtain purely rare, smooth trigonometric coefficient that can be evaluated by the CPU in a single step without any loops. Of course, mathematical elegance must be backed by control theory stability. We formulated a scalar Lyapunov candidate function based on the orientation tracking error. Because our analytical framework inherently captures structural damping, the real parts of our computed eigenvalues are strictly negative. Consequently, the time derivative of Lyapunov function is always strictly negative. This mathematically guaranteed the global asymptotic stability of the URF attitude. The drone is naturally attracted to its equilibrium. Let's look at an extreme physical application. An autonomous underwater vehicle or drone (AUV). Water viscosity imposes several hydrodynamic drag, making the tracking matrix highly asymmetric. If we simulate a 300-second deep sea mission, the difference is striking. A standard numerical integrator accumulates round of errors. The determinant of the rotation matrix drives to 1.04. The software physically swells, perceiving a deformed reality. With our analytical method, the determinant holds at exactly 1.0, absolute machine precision. This geometric structure of our SO3 is perfectly preserved. Theoretical precision is great, but does it run fast and embedded hardware? We benchmarked this framework on standard Pix-Hawk architecture using an ARM Cortex M7 microprocessor running at 418 MHz. A 15-step Taylor expansion requires about 4,500 CPU cycles. A Rajgutta 4 integrator takes 3,200 cycles. Our Theta-1 analytically method requires only 420 cycles. It executes in just 2.4 microseconds. This is over 10 times faster than classical approaches, allowing the attitude control loop to refresh at a frequency exceeding 400 kHz. Beyond the continuous time, our framework also resolves discrete time predictive control. For algorithms like long-range path planning, the flight computer must project the drone state and step into the future. Using the exact same Cayley-Hamilton methodology, we formulate the discrete power equation A to the power of n. This allows the drone processor to jump directly to the future state at time t equal n delta t in a single execution cycle. We completely bypass intermediate matrix multiplication, eliminating all cumulative tracking error. For software engineering, the implementation is incredibly lightweight. Here is snippet using the Eigen library in C++. Notice the absence of for loops or while loops. The offline constants are pre-calculated. The trigonometry functions are evaluated once, and the matrix is assembled in single theta1 operation. It is essentially plug and play for modern Pixar or Betaflight firmware. To conclude, this research provides definitive mathematical unification. We have successfully generalized the rigid body rotation model beyond skew symmetric limitation of Rodriguez formula. By shifting from iterative numerical loops to an exact theta1 scalar layout, we guarantee derived free integration with absolute machine precision. For our future work, we are already extending this analytical baseline to tackle asymmetrical moment of inertia cross-coupling for the active stabilization of satellites. Here are the selected references supporting the framework, including our previous foundational work on 2-2 or 3x3 matrices. I want to thank the organizing committee of APEX and the National Technical University of Athens for hosting us. Thank you all for your attention. I would now happy to answer any question you might have.